Okay, so we're going to get started, I think, this time. So hi, everyone. I'm Luis Lehner. I come from Perimeter Institute. And my task in this set of lectures is to tell you a little bit about how astrophysics meets the dynamical strong field GR. So I'm borrowing kind of a slide from a talk that Rob Myers gave last week, and that was about quantum information. It had nothing to do with this, but the analogy here works as well. So I'm thinking a collision of both general relativity and astrophysics, mainly because in some sense the study of dynamical GR has progressed till very recently very detached from astrophysics questions. But I mean, since February of this year, when LIGO announced the detection of gravitational waves, we're now quote unquote true astrophysics, though some people might want to see a lot more before we actually get to have that name attached to us. And astrophysics for a long time has been working with a regime where either gravity is very mild, or you can use or assume some solutions that were obtained in general relativity for stationary regimes. And so the gravity did not change by and large. But now, because of several reasons, this collision of general relativity and astrophysics is coming to the front, and I'll say a few things of why. And therefore, it really is required for us to, at least in some scenarios, to consider combining both things. And then this nice collision of two cars is actually it's a metaphor for where the field is. In many respects, we're trying to collide things. Things are flying up in the air, and in some sense exciting because you don't know where things are going to land. So some of this debris might land nowhere that is important. Some of it might be quite relevant for some of the questions that the insurance adjuster might want to answer. And so this is where we're going. So in the context of why is it we care so much about astrophysics and what matter or magnetized matter might be doing in these scenarios where you have very strong dynamical gravity, has to do with the fact that even though we might be seeing gravitational waves from a very large number of very interesting systems, and those gravitational waves provide unique information of them, they have intrinsic limitations as far as the physics we can get out of them. And those limitations are, at this moment, mainly tied to the characteristics of both the systems, but more importantly, characteristics of the detectors that we have to go after these gravitational waves. So we know, for instance, that LIGO at kilohertz and above frequencies has a noise curve that grows linearly. So the higher the frequency you go, the less information, or the harder it is to get relevant information from these systems. And just to put things in perspective, if you collide two neutron stars, the merger takes place at above the kilohertz range. So right when things might get the most interesting, LIGO stops hearing. And the combination or the information that might come from electromagnetic counterparts or, say, neutrinos might be fundamental in even answering some of the basic questions we want to go after. Also, the sky localization of LIGO and Virgo, even combine them, which might happen next year, will give you a rather poor localization in the sky for astrophysical kind of standards, 5 to 20 square degrees. And again, an electromagnetic counterpart will help here a lot. And in addition to connecting with obvious astrophysics, like trying to understand the origin of gamma ray bursts, connect with possible observations of kilonova, etc., I said even answer fundamental questions like what is a true theory of gravity? How is GR maybe showing its cracks as to describing what gravity is doing in these regimes, might actually require input from electromagnetic observations because of these reasons. Because at some point, LIGO stops being a good device to detect in the systems. And as I said before, so people in astrophysics have been considering strong gravitational effects in astrophysics, but these have been largely tied to the few analytical solutions we know, and by and large, these analytical solutions have been very limited in scope as far as what may be going on in the systems that are of interest for gravitational waves. So a few examples. So we know how to collide black holes in the computers, obtain these gravitational waves, which then are used by LIGO to try to come out with a detection, and more importantly, to do parameter estimations. But more interestingly, in the larger context, we want to know as well how these black holes may be affecting perhaps gas or material around them. And this is a picture of the collision of supermassive binary black holes that may be interacting with gas in their environment. And that triggers possible interesting behavior. And this is a simulation that shows two black holes coming together, interacting with a plasma, things that will be discussed by Charles Gamy next week. But now, the moment you put these two objects together and the dynamics, you might find out new phenomena like jets or dual jets in binary black holes, and actually poking a little bit on the understanding of jets in single black holes, because it used to be that people thought jets were powered by the rotation of a black hole. Now we know that's only a subset. A black hole, even without spin, moving through a plasma can trigger these jets formation. This is just to tell you a little bit about what this simulation is showing. It's showing two black holes that have no spin whatsoever, and just the fact that they're rotating around each other, the dynamical changes in the space-time are allowing the plasma to tap onto that rotational kinetic energy and powering these jets. We also would like to understand how, say, binary neutron stars merge. This is a simulation that shows the late stages prior to coalescence, the merger, and what happens afterwards. You have a lot of ejecta coming out. Velocities the typical velocities in the system go to about a large fraction of the speed of light. And the behavior of this matter, or the massive neutron star that you form and the ejecta that you throw out is very important in some of these counterparts. As well, you may consider what happens with the magnetospheres that are surrounding the neutron stars, and this simulation that will show the Poynting flux that comes out as these magnetospheres around each individual stars get compressed through the merger, which also can power some interesting phenomena. And this is just some simulation showing a couple showing the interaction of a black hole and a neutron star. And just showing some of the details. For instance, here you see the outer layers of the stars being stripped and accreting to the black hole, which is, of course, shown as a square box. This is just joking here. The black hole is a sphere surrounding it, and here you're excising the area of very, very high curvature that is inside the black hole, where you have to do something special to prevent the computer from crashing, or the code from crashing. And also what you saw going around was this adaptive mesh refinement adapting itself to the properties of the solution to try to capture what is going on. But today, I'm just going to describe a little bit of the gravitational side, what goes into doing this. I'm going to skip, by and large, what happens with the matter, the plasma, or whatever, and I'll tell you why we're able to do that. But in just one slide, I'm going to just try to summarize what the community went through a process of about a decade, where we basically went from trying to use the fanciest numerical algorithms out there in the particular formulation that we were trying to use, to throwing it completely away, going absolutely to the ground level and trying to build everything up, because we realized there were many, many ingredients had to be dealt with before attempting to do so. So this is an example, this is by Franz Pretorius, that shows, for instance, for a particular formulation, which we'll describe, how the ability to control constraint, plus a whole bunch of other things that we'll describe as we go along, makes a huge difference in just evolving a single Schwarzschild black hole. So here we have a black hole sitting in the middle. The black hole is the simplest one that we can think of. There's a spherically symmetric, non-rotating black hole that has some given mass. You have several mesh refinement levels. And on the left side of this plot, you have the result of just using a formulation that is almost as good as it can be. It has all the mathematical properties that you want, but doesn't do anything with respect to the constraints. And on the right, it's exactly the same formulation with some treatment of the constraints that we'll go through. And as you play out, well, you'll see what happens. The errors grow so fast that this simulation after 10M or 20M just crashes. Well, this one keeps going, stabilizes, and gives back the solution you expected. So our task today is for you to understand what goes in and how much you have to worry about some of the things we do. In the process, I'm also going to be just touching or bothering some spherical cows, some sacred cows in astrophysics. Things that, as Jim discussed the other day, that you should not do. I'm actually going to go and mess up with those things, because I'm going to take kind of the main guidance. He said, I want to make sure that I control gravity. Everything else I can think of or worry about afterwards. And I'll tell you why those things are in explicitly as we go along. So this was it as a motivational part of the talk. I'm going to throw out this and then go to the blackboard. So I'm going to go slow. I recognize that maybe many of you probably have never seen or never worried about what would happen or what it is entailed in trying to understand gravity from a dynamical context, how we jump from a very beautiful set of equations described by Einstein to something that you can actually put in the computer. And so please stop me if at any moment I'm using things that you're not familiar with. I'll try to define everything that I need as we go along, but I might miss a few things. So I said our goal is to now concentrate on scenarios where fields are strong, but not only strong, they're also dynamical. So it's not enough for us to consider that we have a black hole that is quiescent, because that black hole will actually be moving around at fast speed and actually might encounter another one and do a collision. Of course, I should also say that if you are in a situation where you can avoid the dynamics, by all means do something else. Use a fixed background or some other approximation. Some people that know me, you might have seen me cringe when people mention Paczynski Vita, and I cringe every time I hear it. But if you have a problem where you can get away with it, by all means, give it a try. If not, then just try to follow these basic things that we'll discuss today. So I have in the second page or third page of my notes one thing that I think would be, or I use as a guiding principle. Theorems are permanent, tricks are ephemeral. By that I mean every field in computational physics have a whole bunch of bag of tricks, and some of those are very useful and very fundamental and have been used very successfully for a long time. So never argue with success, but every now and then question it. And so I'll give you one example of that as we go along, but this is, in my case, will be the so-called constraint transport. And I'll tell you why is it that trick is absolutely necessary, but if you take a step back, maybe it's not so sacred. But so the theorem I want to kind of base everything on is a theorem by Hadamard. And it basically says any physical set of equations that you consider is this set of equations that determine the physics of your system, and I'm thinking of a hyperbolic system in particular, but it is generic, must be well posed. Or actually, here I'm abusing notation, the system is not well posed, the problem you're trying to solve with this system of equations should be well posed, and that means it has to satisfy three conditions. One is the existence of solutions. The other one is the solution for the right boundary conditions and initial condition. The solution is unique. And more importantly, the solution must depend continuously on the initial data, or continuously on the initial boundary data. So what do we mean? So mathematically, generically, we mean the following. Suppose by U, I denote the solution or the norm of the solution that may have many, many fields. Just imagine a global norm, a global non-negative definite norm with respect to the fields of your solution at time t has to be bounded by whatever you had at time t equal to 0 times some constant, and you're going to allow for an exponential as well, e to be t. And k and beta, these should not depend on initial data or boundary data. So if you have a system of equations that you show that does not satisfy these, you should be throwing it away, or you should be thinking, what can you do to fix it? Because it shouldn't be possible. It shouldn't be a possible system describing any physics. So you probably are not aware of these, but in cosmology, it's very often the case that people try to write down theories to replace Einstein's equations of general relativity, and by and large, most of them do not satisfy these conditions. There is a reason why, but if you try to put that in the computer, it will just blow up in your face immediately, and you're not going to gain anything out of it. So we're going to use this theorem quite a bit. So let me just also tell you something important, which is a sufficient condition. So now I'm going to restrict myself to a hyperbolic problem. So a sufficient condition for well-posedness is that if you write your system in such a way, again, I imagine that I have a vector of all the unknowns, and it's governed by an equation that goes like so. So imagine that you have been able to write the system in such a way. This is, so for instance, hydrodynamic equations. You can write them this way. If you write Einstein's equations, you can show that you can, or Maxwell's equations, you can also, by introducing further variables, you can define them, or you can derive them, or write them in first order form. And so this piece, the piece that has the highest derivatives, in this case first order, it's called the principal part of the system, and everything else is called the rest. Of course, this A might depend on the fields themselves, but what you're doing, again, just reiterating what was said on Monday, you can imagine that you pick an arbitrary solution that you may not even know. You assume there is a configuration that is a solution to your problem, and then you imagine linearizing with respect to it. So this thing with these matrices will depend on your background, but the properties of this matrix now is what you're after. The rest you don't care about. The rest will determine particular solutions, but the main properties of propagations are determined by this part, which is the principal part. So the sufficient condition for well-posedness is that this matrix here is diagonalizable. So there is a complete set of eigenvectors, and the eigenvalues are real.
So sorry, you're assuming that the leading part is first order?
No, I'm not assuming. I'm saying I can reduce it too. So I can take Maxwell's equations.
Can you do for us a simple case like the scalar wave function?
Yes.
How do you put it at least one?
Yes, so let's do that. And for simplicity, let's imagine that we're in one dimension. So suppose I have, right? So let me define now, introduce two new variables, f to be u comma x for historical reasons, g u comma t. So now my system of equations becomes u comma t equal g comma t, f comma x, f comma t, g comma x. So this is my new system. And now my equation gets written as u g f comma t equals 0, 0, 0, 0, 0, 1, 0, 1, 0. And so the requirement, the sufficient condition for well-posedness is that this matrix, or that matrix, each individual one, is diagonalizable, the eigenvalues are real. If the eigenvalues are not real, then it cannot be well-posed. And if you do not have a complete set of eigenvectors, then what you have is something called a weakly hyperbolic problem. And weakly hyperbolic problems are almost as good as it can be, but not quite. And the problem is the not quite. And so an example, which I have in the notes, is this one. I mean, I'm sure, or if I were sitting where you are, I would be wondering, when is this guy going to get to the gravity part? Hold on, we're going to get there. But I'm just kind of telling you, so in Argentina we have this old saying that goes something like, if you have ever burned your tongue with hot milk, you'll cry at the sight of a cow. We have burned ourselves so much that we actually went all the way to here to understand the problem. From there, we build ourselves back up. So let me just give you this example, which is, so imagine that you have two coupled equations. They seem to be very simple. If we write it in this form, it's written as 1, 0, 1, 1. And this is very simple enough that you can just iterate. And the solutions are given by this. So let me just, U is given by, so I coupled it differently in the notes. So let me just. So this is a very simple enough matrix that you know already by just taking a look at it, what the eigenvalues are. So the eigenvalues are 1 and 1, but because there is a 1 sitting here, if you remember your linear algebra, there's a Jordan block, it tells you there is only one independent eigenvector. So what are the consequences of that? Well, when you look at the solution, U is given by the functional derivative, so let me just write it this way, with respect to the argument, of some arbitrary function that, of course, is determined by the initial conditions. Let me call it f1 of t plus x times t plus some other function t plus x, and v is some function 1 of t plus x. So if you think of constructing the norm, just imagine u squared plus v squared, the absolute value, take the square root, you're going to see that this solution will be growing with time. If we imagine that we have taken these functions to be kind of sine and cosines, for instance, then you know that you will be able to bound these things by 1. So at worst, you'll have over there that the absolute value of u of the norm of your solution is bounded by the initial data times something that grows as t. And so that's pretty fun. So this is well posed. So we have a weakly hyperbolic system, and the solution is well posed. But remember, one thing that sufficient condition says, we ask conditions for the matrices A, but we said nothing about the rest. And that's a good thing. That's the difference between a weakly hyperbolic problem and things are called strictly hyperbolic, strongly hyperbolic, or symmetric hyperbolic, and Jim alluded to that in his talk. Which is, in the case of strongly, strictly, or symmetric, you don't care about the rest. In the case of weakly, you absolutely care about the rest. In fact, you can see that if I couple these by simply using, imagine the rest is just that. So we add u here. Sorry, this should be a v. Yes, this should be bx. If you simply add u there, all of a sudden the solution completely changes. And now, let me just write it. You're going to have for v, for instance, the solution goes like c, e to the c1 t plus x times some other constant which you can absorb, e of t square root of c1. Doesn't matter. But now what we have is if we were to evaluate the norm, we have a growth that knows about the initial data. And that's a big no-no. Because now you can imagine someone giving you a configuration, and in some initial configuration, someone else picking another configuration that is arbitrarily close to the first one, but it has a little bit of energy difference arbitrarily high in frequency, then you can have the solutions at a later time completely diverging from each other. So you have no control on how close a solution that is arbitrarily close in principle to the configuration you want will give you a solution that is in no way expected to be sufficiently close to the solution you're looking for. And this is crucial with numerical applications because the initial data that you consider is never exactly the initial data that you want. It's just at best a round of approximation to that you wanted to study. And so we got to this is an extremely simple scenario. We have very simple eigenvalues. We had a very simple right-hand side, and yet we ended up with something that is very nasty. So why would we think that if we have a weakly hyperbolic system in a system that is as complex as general relativity, would we be lucky enough that the lower order terms, the rest that I call there, would be sufficiently tame that it will not give us trouble? Of course, I should stress that we said sufficient. It's not necessary. In fact, there are examples where the lower order terms are sufficiently tame where you have a solution, but in general, you don't know. And so, again, using the fact that we don't want to burn our tongue again, we want to start with the strongest possible scenario and then go from there. So now let's try to go back to, or let's try to go to gravity. I'll do something here. So some general statements. So in order to study or to determine how we're going to study a system of equations, so you've seen that Einstein's equations say you can write them in this way. And so it will look like we have to worry about everything at the same time. But there is something that we can take a page out of that and use in the following. So let me just kind of anticipate some of the things we're going to discuss. But you can also use your intuition. You know that gravity, even in the Newtonian regime, is governed by a second-order equation. We have the Poisson equation, so you expect that the part that knows about gravity, which is the Einstein tensor, has second derivatives of g. While this part, for many cases of interest, has the fluid variables, let me call them F, and the metrics variables, and the equation of motion of your fluid is given by the conservation of stress energy tensor, which in the left-hand side is understood as the Bianchi identity. But importantly, if you look at what this equation entails, it entails derivatives of your fluids and at most derivatives of your gravity tensor. And we'll look into that in just a bit. So now what we know is that the left-hand side has second-order derivatives of the metric. The right-hand side, or the equations that will determine the right-hand side, have only first-order derivatives of the metric. So if we do that trick that Ed asked me to do, to introduce some new variables to reduce everything in first order, what we'll find out is that the first derivative will have their own variables. Those variables are not differentiated, and therefore they belong to the rest. So as far as the equations of motions of gravity are concerned, the fluid appears undifferentiated, so it's part of the rest. And as far as the equations of motions that determine the fluid, the gravity part comes at the one-order derivative fewer than that determines the evolution of the gravity itself. So it is also part of the rest. So as far as we are concerned, with respect to perturbation, the behavior of perturbations with respect to any arbitrary configuration, we can treat them as decoupled. So we're going to concern ourselves with the gravity part without worrying what the TAB is doing. Then we're going to concern ourselves with the evolution of the TAB without worrying about what the G is doing, because at most what they are doing is introducing a rest. That rest, of course, is absolutely important in determining the particular solution, but it's irrelevant with respect to how the perturbations of the fluid or the metric will behave with respect to any particular solution. So that gives us a license to just ignore one side of the equation when we discuss the main properties of the solution. Which is convenient because now we're going to just study or discuss how we're going to consider the evolution of the metric tensor itself. Okay, so before we do that, we need to kind of set up a common ground set of rules, which is kind of the basic tenets of general relativity. So we know that in general relativity, gravity is not a force. We're going to describe the effects of gravitational forces by understanding that the manifold where any event takes place is curved. And the curvature will be encoded in something that we call the metric tensor. Which with it, we're going to then define or use it to define or calculate distances. Just this way. Very quickly, I'm beginning to introduce a notation with you where we're going to denote explicitly vectors, tensors, etc. with indices. This is called the abstract index notation. So here I have an object that has two legs, if you want. So this is, if you want to interpret it, it's a matrix. And when we contract it with vectors, it's a displacement vector along A, which is generic. I haven't specified what A is. Then we construct a scalar. So here, we're also using the fact that if we have two indices that repeat, we add them. But we have to be very careful that we add them in the right way. So this makes sense, which will be like V0 plus V1. I'm also introducing that A goes from 1, 2, and 3. So we put a 0 there to stand for what we're going to call in not too long time. In between quotes. And then we reserve 1, 2, 3 for the spatial parts, which we still haven't defined what those are, but we're going to get there. We also need to understand that now we have a curved manifold when we take derivatives. Just as we have to worry about the change in the field in flat spacetime when we take, say, a partial derivative, now the natural derivative needs to know not only about the change in the field, but the change in the curvature, which can introduce change itself. So we're going to introduce a derivative, which we call nabla A, which is the covariant derivative. So derivative that satisfies all the properties you want from a derivative, so it satisfies the Leibniz rule, but it also, in order to pick the unique one that satisfies our property, we're going to demand this is 0. So it's a derivative that is compatible with the metric tensor that is describing our curved manifold. So as a result, when we take derivatives of objects, we pick up perhaps new terms. So in particular, if I take the derivative of an object that I'm calling VB, notice that I'm beginning to to note that there is a difference between where this index is in the upstairs side or in the downstairs side, and I'll tell you what the difference is in a second. But this is a tensor, so this is a vector, and the derivative, the covariant derivative acting on the vector, gives us as a result the partial derivative of the vector. This is what we would have had in flat spacetime, but there is another contribution. given by so. This is the Christoffel symbol. This encodes or knows about the fact that you may have coordinates that have kind of divergences, or they're not, say, exactly in a square grid, and they might not be in a square grid because you either chose coordinates that may be different, like, say, if you're using cylindrical coordinates, so gamma knows about it, but also if you have curvature, gamma will know about it as well. If you take the derivative with respect to a scalar, that is just the same derivative that you would have written before. That's the spatial derivative. And if you take the derivative of an object that now has the index down, by definition, an object has the index down, it's raised and lower with respect to the matrix. So this takes a vector and produces a covector or vice versa. And so this is similar to what we had before, except that there is a minus sign. So I have to tell you what that gamma is. So it's the so-called Christoffel symbol. And out of that, we can construct a very important tensor, which is called the Riemann tensor, the curvature tensor, which is defined like so. So this tensor knows about the curvature of the spacetime in more than one way. So let me just give you a couple of examples. So suppose you had two unaccelerated otherwise lines. So imagine you have two curves. They may be getting closer together or further apart because they are on a curved spacetime. So let me imagine that we live on a sphere. As you could start from the equator, two lines, and you know they're going to begin to converge. So if you compute the relative acceleration of these two lines with respect to each other, you find that the acceleration is given by this guy. So let me just write it. It's in the notes, it's succinctly there, but there will be the acceleration goes, and that's a vector, goes as r, a, b, c, d. Oh, let me use a different symbol. Say. So it says that the x, oh, sorry, it should have minus. So the acceleration in between these two lines over there knows about the Riemann tensor. The velocity along the lines, so this C is So if lambda parameterizes my curve, this is the velocity along that curve, so it knows about the velocity at which you're going along the tangent, and this vector, so this should be xb, no xb. This L is a vector orthogonal. And it also comes in, if I imagine taking, so let's do this exercise. Suppose we take that triangle on the sphere and imagine having a vector pointing in some given direction, and let's try to parallel transport it around the circuit and bring it back. So suppose the vector is pointing that way, so we go along this. When we get to this point, it's pointing this way, because we're just going along that line. Then we come down this line, then it's still pointing in that direction. And then we take it back along this line and then bring it up again. So this vector now is going to be pointing that way. And again, that is because we have done a curve around the curved spacetime. If we were doing this in flat spacetime, of course, we would come back and the vector would be the same. And this is called the commutator of derivatives. So if there is this relation that also defines the operation we just done. Anyway, so out of this tensor, Einstein constructed the equations of motions for general relativity, which are, as we said, over there, GAB equal A pi TAB, where GAB is equal to RAB minus 1/2. This is the so-called Einstein tensor. RAB is R, D, A, or C. And R is G, A, B, R, A, B. And this is the tensor that satisfies, if you take the divergence of G, you have 0, which is what you needed, because the right-hand side of that equation, you know, if you want to put TAB, the conservation of stress in a tensor implies the divergence of that tensor equal to 0. So now that's our starting point. We want to know how can we turn those equations into something you can put in the computer. But the problem is already there. Those set of equations are covariant. There is no special rule that tells you this is where you have to put initial conditions and this is where you're going to evolve to the future. There is nothing in the Einstein. Einstein worked really hard to not have to do any particular, make any particular contact with any particular set of coordinates. So we have that problem. That also brings a separate problem or a related problem to what we already talked about. We know that because the metric tensor or the solution to that equation or this equation is covariant, does not necessarily know about any particular set of coordinates, you know that two solutions could vary with respect to, say, the difference in arbitrary many ways. Just because you can take any solution, do coordinate transformation, you will have another solution to those equations. But then if you want to compare the two metric tensors, they will be vastly different. So in a sense, we already start with a problem that is ill-posed from the get-go, unless you choose coordinates. So we're going to have to find a way to have the right framework that allows us to identify which coordinates we're going to choose. Okay, so the first thing I'm going to describe is the so-called ADM formulation. And it's the ADM formulation at York, because there are a couple. One that has been the one mostly used in the early attempts to quantize gravity. This is the is a related version to it, which was mostly used at the beginning to set up the initial boundary value problem of general relativity. So we need to address first the issue of how we're going to choose coordinates. So suppose you have your spacetime. Let's imagine the blackboard is our spacetime. And now choose arbitrarily some foliation of the spacetime with respect to some given set of hypersurfaces. So I'm going to imagine these are hypersurfaces. We still haven't said anything about what the character of the hypersurfaces are, but we want to make contact with the thing or the concepts that are the closest to what you have already been seeing in, say, astrophysics, where we have been assuming Newtonian theory somehow provided a special time for us and a special set of slices. So we're going to imagine that these slices are, which I'm going to call sigma t, let's say sigma t2 and sigma t1, are space-like. So there are many ways of understanding how a surface is space-like, but the most natural geometric one is to imagine, suppose the normal to this hypersurface. There's a vector, let's call it n. So if n is time-like and is the orthogonal space to it, it's going to be space-like. So we're going to ask NA to satisfy this condition. And the fact that we have a -1 is because we have already chosen a particular signature to our metric. And by signature, I mean, where do we stick a minus sign? So we're imagining, say, in flat spacetime, so Minkowski. Because we stick a minus sign in there, that's where we have this condition, that the norm of this vector is -1. And remember, we have to have vectors with norm that could be positive, negative, or 0. If they are 0, they are along light cones. If they are negative, they are inside the null cone, and that's it. They are pointing towards the future. And if they are positive, they are outside the light cone, and they are space-like. So that's the first concept we introduced. Each of these slices, we're arbitrarily going to assume that we're choosing coordinates such that along all on that hypersurface, t is constant. So we're beginning to put or bring in the concept of time, an arbitrary time so far, in our language. Also, because this is a surface now that has t equal constant, you know that the normal to the hypersurface, just using basic geometry, is given by the derivative of that variable. And because this is a scalar variable, we could be using this derivative or that derivative, because we already said that when you act on a scalar, the covariant derivative gives you the same as a partial derivative. So let's introduce another, the first non-trivial concept, which is suppose the coordinate time difference between t1 and t2, which is t2 minus t1, once you go from this point to that point, which we're still not labeling, we just say just pick a point, find the normal, go straight to the normal till you meet the next hypersurface. You can ask, what is the proper time? What is the time that an observer that does that with you would measure its clock tick? Typically, that observer will not see delta t, will not see t2 minus t1. What that observer will measure is something else, and which is proportional to t2 minus t1. We're going to call the proportionality constant alpha. So this is the so-called lapse function. And of course, it's called lapse because it gives you a sense of how much time elapsed as you did that exercise. We so far have said nothing about what labels we're going to give to that point, but we have arbitrary choices. So let's imagine that we give label x, y, z to that point. We could choose to give labels x, y, z to the point we meet if we go in the normal direction. But let's imagine that we give those labels to a different point. This one here. And so we imagine that the flow of time, if we keep coordinates constant between this point and that point, this is the flow of time. So this is the vector we're going to call d dt, which is going to be the time or the flow of time that we're going to associate to the standard time that you have used, say, in Newtonian theory. But now we want also to keep track of the fact that if we went along the normal, we would have landed here. If we went along the time flow, we would have landed there. So we're going to introduce another vector here that measures this separation. This is called beta A, which is, again, for obvious reason, referred to as the shift vector. So now we can use these new concepts that I introduced to rewrite the metrics in this way. So the metric tensor that we have defined somewhere, where was it? I don't know. There, yes. This metric tensor that we had here, where all coordinates kind of were standing in the same footing, now we're beginning to split it up. And the 0, 0 component, if beta were equal to 0, we'll be measuring precisely this time, this elapsed time. So we can write it as this way, minus alpha squared dt squared. And then the rest measures something with respect to the intrinsic geometry to that slice. So this metric tensor hij now is a metric tensor of each individual slice. So now we know what we have done is split the full metric into something that lives intrinsically to each hypersurface plus some concept that connects one hypersurface to the next one. So those will begin to represent the main quantities that we'll use later to write the equations in a form amenable, at least in principle, for computation. So now if we just identify, we find out that there is a relation between the metric tensor G of the full spacetime and the metric tensor, and let me just write it slightly different, of the individual hypersurfaces by so. So this is the individual matrix. So if you want this NA and B contribution here is precisely what we have to subtract from the GAB to just leave at the end of the day the intrinsic metric that we can use to specify distances and curvature of those individual slices. H also satisfies, this tensor satisfies a few other properties, which you can quickly and easily check. So if you do HAB, HBC, so remember, every time you have an index anywhere and you want to place it anywhere else, you have to hit it with the right metric component. So just here, remember we said that. So if we wanted to raise it, we multiply by the matrix when the index is upstairs. If we want to lower it, so if we want to lower it, this is the other way around. So we raise with the metric when the index is up, and we lower with the matrix index is down. So the same thing you would do here. So you can easily check, given the fact that this is normal to the hypersurface, that this is equal to HAC. So this is if you want to think in terms of operators, this is an operator which, if you consider the square of the operator, it gives itself back. So that's one particular property that we're interested in. Second, HAB, hitting n gives you 0. And third, HAB, hitting a vector, let me call it T, give you TB, or S, let me just call it S. So if we have a vector, and any vector that is orthogonal to the hypersurface, the action of H acting on that vector is 0. And if we have any vector that lives on the hypersurface, the action of H acting on that vector gives you back the vector. So these are three properties that basically tell you that H is a projector operator. So any vector that might live in the full spacetime, hit by appropriate number of H's, depending on how many elements it has, will give you something that's completely tangent to the hypersurface. And this we're going to use now. So let me define one last concept, and then we can begin to move on.
You're summing over B, why do you still have B on the right-hand side?
That's a mistake, that's an A. Thank you. Yes. Thank you. So we need one more concept. So we know that we can kind of foliate the spacetime with a series of hypersurfaces, what the metric of each hypersurface. But now we'd also like to have the knowledge of how that hypersurface is embedded on the higher dimensional hypersurface. So suppose here around us we're in flat spacetime. This sheet, if I take it like this, is flat. But of course there is a difference between this and that. As far as it's embedding within the higher spacetime, we need this concept. How do we measure the fact that this surface is curved? And that's the so-called extrinsic curvature. So let me define it first. I'm going to put a minus on here. So if we take the covariant derivative of our normal vector, we change the sign. This is a convention. This convention is chosen so that if, as I say here, the surface happens to be concavely immersed in the higher spacetime, it gives us a positive curvature. Otherwise, it gives us negative. And we're going to stick in here, and because of convenience, I'm going to do it this way. By this is nothing but the H with the appropriate indices so as to do the right projection. So let me just rewrite what I have in here, and quickly I'm going to just begin to switch to that symbol. So that would be having KAB minus HA HB alpha beta. So here there was a bit of abuse of notation where I have the same indices in the right side and the left side. This is commonly done, but in reality what you mean is that you had other indices here that when contracted with the right indices of the projection produce the indices that you have in the left side. So this is the extrinsic curvature. And the good thing is that the extrinsic curvature now can be related to what the spacetime is doing, what your coordinates were, and the rate of change of the intrinsic metric to the hypersurface. So the definition, I'll give you the definition, is so I have just because of lack of space, this is in the notes. What you can show is that this K, defined this way, is related to the time derivative of the intrinsic metric as you go along the flow, plus some corrections that come with respect to because of the fact that we also are shifting coordinates as you go along. So of course, if you have chosen coordinates conditions such that the shift is 0, then the only relation you have is that the time derivative of h is equal to the extrinsic curvature times perhaps the fact that the time change, the time elapsed with respect to the proper observer is slightly different than just delta t. So the notes tell you, but the important thing is to know if you know k and you have introduced your coordinate conditions, then you know the time derivative of h. And now we're ready to write the equations of the Einstein's equations in terms of something that begins to look like something you could put in the computer. Question? No? So we go back to these equations. I'm not going to show this derivation. This derivation actually can be found in lots of places. I gave you a suggestion. There is this numerical relativity book by Miguel Alcubierre that is actually very nice. There are several other numerical relativity books out there. There is one that is actually pretty good. Let me not say which one, that I can give you in private. But it says there that numerical relativity is the art of putting Einstein's equations in the computer to solve astrophysical problems. That's incorrect. That's only a subset of things you can do if you actually put Einstein's equations in the computer. Other than that, the book is pretty fine. So then you do that, you take this, and then you decide to consider different projections. Because now we have a vector. Right? Imagine you have a vector S, or let's just call it a vector v, A. If I dot it with n, right, this gives me v along the normal direction. If I take v, A, as we discussed, and we dot it with hb, this gives me the v parallel, the component of the vector v that lives on the hypersurface. So we can do that with any object that we have, in particular if we have tensors, we do the same thing with just adding more h's, as I said. So if we take this equation and you dot it with n, a, and nb, what you get is the following. It's 3. I'm going to put a 3 here and tell you what it is. So there are we're defining several things in one line here. First, when I put 3 here, this is the Ricci scalar associated to the 3 metric of the hypersurface. So this is the same as the one we wrote before, R somewhere, the Ricci scalar, except that now you do everything with respect to 3, the quantities associated with H. So this is computed out of H. Doesn't know anything about the full G. This is K, the extrinsic curvature. So we have defined the following, and I already put in I and J here. Once we have the right to define things on the hypersurface and off the hypersurface, then it makes sense to add different variables to just keep reminding us that an object only lives on the hypersurface. Remember, we defined the K by fully projecting it to the hypersurface. So I can use I and J, and now I and J run from 1 to 3. We don't know anything about the 0. And so this is Kij, Hij, so it's a trace of the extrinsic curvature. Of course, because it lives on the hypersurface, we take the trace with the object that lives on the hypersurface. That's the metric. So that's K. And here we have just a contraction of Kj. And you see rho here. This rho need not be the rho that you write in, that you have been seeing so far. This is the rho that the right observer, the observer that is flowing with n, would measure. So rho is defined as TAB and A and B. So the observer is going normal to the hypersurface, measures that energy density. if you choose a different observer, you could have used contracted not with the normal, but with T, TA and TB, you would have had a different rho. So you have to be mindful of how is it that you're defining things. So this is called the Hamiltonian constraint. If for simplicity, you imagine that you have a flat, a metric that is flat and is embedded in a flat manner with respect to the higher dimensions spacetime, then K is 0. So this is gone, that's gone. And R, we can see that it's related to, if you imagine that the metric is flat, but has some small curvature due to, say, the gravitational pull of this energy density, then this is related to, with the right factor, the Laplacian of a scalar field. So you here in this equation is Poisson's equation. Now we can imagine taking a dot with respect to n and say HC B, or n. Yeah. Then the equation that you get is the following: dB so this is conservation of momentum. This d is the same as the nabla, but for 3 dimensions. So dB of H AC is equal to 0. So this is the intrinsic covariant derivative to your hypersurface. So it will measure how, or it will tell you how to take the derivative on an intrinsic 3-dimensional hypersurface that may be curved. Again, if the intrinsic dimension, like hypersurface, is flat, then this d is just the standard covariant derivative. But of course, in this case, the metric will be flat, and then you'll be getting, and this also will be 0. But here you have this just a partial derivative, and this will be an identity. And this j, well, is again what an observer along the n would measure as momentum. So g a is minus and I already used that notation. So it's take the t, dot it with the n, and whatever is left, project it to the hypersurface, and that's what you define by j. So, but notice now what we have. Both these equations, let's count derivatives. So this is the curvature, this is the metric tensor, the curvature tensor with respect to the intrinsic metric h. This will have only spatial derivatives, so there is no time derivative here. Here there is a time derivative because we said what k was, but it's just a first order time derivative. So this is first order in time, first order in time. So the highest time derivative you have in here is just first order in time. Everything else is a space derivative. And similarly here, this is a covariant derivative intrinsic to the hypersurface. There is no time derivative here, therefore, and here there is at most one time derivative. So these are so-called constraints, and we'll see why and what follows. So we're missing one last projection, which is a projection that is completely orthogonal to the hypersurface. And that equation is much more complicated. So if you thought it would, so you project twice on these equations, then you get the following. Okay, so let's pause here and see what we have so far. So this is, let's look at this equation. So here we have h, the time derivative of h was k. So let's imagine for the time being that alpha is 1 and beta is 0. This one tells us the time derivative of k, let's forget about anything that has a beta, let's imagine that it's 0. Let's forget about that because we have chosen 1. And so we have the time derivative of k is a Ricci, so the Riemann, the Ricci tensor, sorry, and then a whole bunch of terms, and then this has to do, this S is a projection of the TAB completely onto the hypersurface. S is a trace of SAB, and rho is what we defined before. So what you can begin to see is that you have a second order wave equation and then some with respect to HAB. Right, so if I take a time derivative of this equation, which is we use in our definition, then we're going to have minus 2 time derivative of k. We can express this, so they will have the second time derivative of h. So hidden in here we'll have second time derivative of h, AB, is equal to RAB, and this one has second derivatives of h, right? So I'm ignoring a whole bunch of things, and some of those were very justified in ignoring because k has only first time derivatives. We said everything that has only one derivative is lower order term. We can ignore that. And so here we have something that almost looks like the wave equation, but we're actually going to get back to it. In fact, it does not. It looks like a wave equation plus a little bit of extra stuff, and that extra stuff is precisely what turns these equations into something that is weakly hyperbolic. If it weren't for that, we would have been home free from the get-go. It was because of the unfortunate fact that this curvature is not just the right operator to have a strongly hyperbolic system. But this is still the base of everything we start with in some sense because of several reasons. One, there is a whole bunch of effort that has gone into finding conditions that satisfy this equation. So again, think of the analogy with Maxwell's electrodynamics. You have the let's imagine also in the absence of sources, you have divergence of E equals 0, divergence of B equals 0. You have the evolution equations for E and B. And what you can show is that if you have initial conditions satisfy the first equations, the constraints, then the evolution equations will preserve the monopole constraint and the constraint of no charge. The same thing happens here. This is the higher derivative part of the equations. This is the stuff that actually governs the evolution. You can show that if you satisfy this at the analytical level, if you satisfy these two equations, evolving with these equations will preserve that analytically. Because it's weakly hyperbolic, as I said, any little deviation on the initial conditions will just vastly differ from the solution you're trying to look for. You also might wonder, well, what else do we need in order to do the evolution? So this discussion we're having, we're assuming that beta is 0 and alpha is 1, but that is up to you. You have to provide the coordinates that you want to use to evolve. So you might think that, well, alpha 1, beta 0 is the natural one, is the one that is closest to what you perhaps have been using in kind of Newtonianly motivated or especially relativistic motivated scenarios. But let's imagine that you have the sigma at some point begins to look like so. So you have some curvature in sigma. So now try to follow the normal to this one, because we said that if you have alpha 1 and beta 0, your time flow goes with the normal vector. So but very quickly, if you follow this direction, then you're going to hit a coordinate singularity. You're going to have a point in your spacetime that is labeled by two different labels. So that's bad. Things will go, you're not going to be able to evolve past that point. So there is a whole art in defining what are the right coordinates or coordinate conditions for alpha and beta to evolve. And we'll discuss just a little bit of this. But before that, let's just deal with the largest problem we have, which is the fact that this system is weakly hyperbolic. And how do we address that issue? For that, let me just now pull back and discuss something more general, which comes under the name of generalized harmonic formulation. and was a formulation that was first used to, actually, it was first used to many things in general relativity. It was used first by Choquet-Broat in the 50s to show that Einstein's equations admitted solutions, at least for some time, given some initial configuration. Was used also first in the evolution of Einstein's equations that successfully modeled the first binary black hole collision by Pretorius, and in a few other cases. But then you might wonder, why is it took 50 years from Choquet-Broat using it in the 50s to prove some rigorous theorems about the existence, at least locally in time, of solutions of Einstein's equations, and Francis using it in 2005 to solve the binary black hole problem. I'll tell you why in a second. But first, let's just take a step back and write what RAB is going to be. And we're going to think first in just the RAB without having to worry about the full Einstein equations, because we can do the following. Let me see if I can do it here. There is a so-called trace reverse form of Einstein equations. So these Einstein equations. And by the way, we're in GR, we always use set as many constants to 1 as possible. So G equals C equals 1 and sometimes 8 pi, or we just shove in the 8 pi in the TAB. So then it's a nightmare to come back and put units, but all along you have an easier ride. So the trace reverse of this is just imagine taking the trace of this equation. So we hit it with G. When we hit GAB here, we're going to have the Ricci scalar. When you hit it here, we're going to have a 4 coming from the contraction of GAB with itself, and we're going to have the T here. But then on the left-hand side, you're going to have R, and the right-hand side, you're going to have T. So there's a way to write this R, the trace, this R in terms of the trace of the trace energy tensor. So the trace reverse form of this equation is nothing but this. So it says that given that we already argue that we can worry about the matter or the content brought in by the trace energy tensor independently for most of the cases of interest, independently of what the curvature is doing. So let's, for simplicity, think of this way, ignore that for a moment, and just consider the RAB. The reason I want to do that is because RAB has a very kind of provocative expression, or there's a way to write it in the following way. So let me just read first. And also for simplicity, now I'm using commas when I have partial derivatives. So this is GCD taking the partial derivative with respect to C, partial derivative with respect to D of the metric tensor GAB, plus, minus 2 Okay, so here I'm going to be very, in the notes is this, we have the complete expression, and then we have dg times dg. So this is what is hidden in this RAB, and I have told you nothing about where, in which dimensions were. This is completely general. So had we use h in terms of g, we would be computing the Riemann associated to the 3-dimensional hypersurface. But the key thing is to notice that we have this. So we have this term and that term. Everything else has at most one derivative, right? And we said that everything that has lower derivative than the principal part, we can ignore for all intents and purposes as far as the general discussion. So here what we have sitting is it's essentially what you would have written in the wave equation in a spacetime that has some curvature, if these were a bunch of scalar functions, right? So this is as hyperbolic as it can get. This is symmetric hyperbolic. It's the most beautiful thing that you could write to second order. This, can I say this is just crap? I mean, this is horrible. This actually breaks anything that you have. So here you have something beautiful, and it would be a miracle that this contribution still leaves something that is hyperbolic. And it is the reason, remember, I said before, did I erase it? It's here. Before we argued that this thing was a second time reduced with respect of HAB, plus these 3 RAB. This 3 RAB would have that piece except they're written in terms of h, which will be, together with this, a very nice hyperbolic piece. But then we would have something like that, except that instead of the nabla, we would have a d, and the gamma would have been the Christoffel symbol associated to the 3 hypersurface. So it is that thing that breaks the hyperbolicity, the strong hyperbolicity. So now you can just do the human nature. If something bothers you, you can kill it. This is what happened in the 50s. So when Choquet-Brois looked at the proving the existence of solutions for Einstein equations, say, well, let me choose this condition. Because after all, how many equations do we have here? So B, how many independent values of B can B take? Any takers? 4, right? So, and we have 4 conditions at our disposal. So you can say, well, choose alpha and beta to whatever they need to be in order for them to be 0. If we have that, then hyperbolicity is guaranteed, and we're home free. So why is it that this hasn't been used, or it took 50 years for people to actually go into it? Actually, it took a little bit less than that, but not for the full problem. The reason for that is that actually there are mathematical theorems. Remember I said trust theorems just question the tricks. So there is a theorem that says, and that actually this teaching in reverse. Actually, you should also have to be careful with theorems. Suppose you have this equation. So this is a scalar wave function with some nonlinear terms thrown in. I stand still saying that for the perturbations, the behavior of perturbations of your solution, you can ignore the lower part. So these are lower derivatives. So imagine that you have time derivative, time derivative, time derivative, space derivative, or space derivative, space derivative. The lower terms in your equations, as I said, determine particular solutions. Well, it turns out that unless these A's are specially or satisfying some special properties, generically what mathematicians have been able to prove with these equations is this generically will blow up in finite time. So you're going to have a blow up in finite time of generic solutions to these equations. Then you look at this equation and say, well, this one looks like that one. We got rid of this one. And this one are time of the first derivative times first derivatives. So that's precisely what we have in here, and that's precisely what we have in here. People saw that and ran away. So basically said, well, there is no chance that miracles do take place. Turns out that they do in Einstein's equations. And this was proven by Kleinerman in the 80s, mid-80s. This is Sergio Kleinerman found the so-called null conditions that show that A have the right properties, and Lindblad and Rodniansky also down the road then redid the stability of Minkowski proof knowing that this property was satisfied. And then it's a much simpler thing to read. Anyway, so that was the first thing that people kind of worry about, that because they knew this result, but not that Einstein's equations were special. The other property is then try to say, well, what does this imply with respect to your coordinates? So this is the same up to a sign to specify this. So the coordinate conditions that would have given rise to this, to the ability to set this to 0 are precisely these ones. And so what you have is a wave operator acting on your coordinates equal to 0. And that was the second worry. Because you imagine that you have coordinates that are governed by wave operators. Any coordinates that you may have will likely fly away at the speed of light. So if at any time you have coordinates that were convenient for your numerics or for your study, very shortly after, these coordinates would not be convenient anymore. So that was kind of the folklore. People, because of these observations, just stayed away. Then slowly people began using it in simpler situations in cosmology. And Franz realized that maybe he should give it a try for binary black holes. That coupled to a whole bunch of other things that had been learned at that time about what were good algorithms, what type of properties you require of both coordinates and system. He put everything together, and then he solved the binary black hole problem. So now we're going to look into that system. The one price to pay, you would think, however, is to say, well, I gave up my coordinates. So maybe this is okay. Maybe the coordinates are so fine, but will they always be fine? Will it always be sufficiently generic for me to try to treat any problem? And the beauty here is that you did not necessarily give it completely all up. You could imagine setting something else. You could imagine saying, this is equal to, how do you write it? So you just say, imagine that the gammas are given by some sources. You still haven't told what those are, so that the coordinates have these in the right-hand side, or maybe with a minus sign. So now, rather than having the 0, you can say, well, I can imagine putting a source by fiat, from whatever direction I want, provided I have some decent sense of what might be good enough, then this equation changes into h. Now I no longer see the second derivative of the metric either, so as far as this is concerned, it's perfectly hyperbolic. Of course, it's now coupled to h, and I still haven't told you what h is, but if h is analytically given, or given by some other nice set of evolution equations, and this is an option, so now I have a hyperbolic system for EH, a hyperbolic system for EG, and then I can go. This example is what I showed you at the very beginning. Remember, I showed you a case where you use a hyperbolic formulation and then the left-hand side just went to hell very quickly. This is what you have. So there is still a missing ingredient in here. There is something else that having a strong hyperbolicity was not enough. And was not enough because of the fact that we have constraints. The theory is strongly constrained by these constraints that I mentioned before. And when you're not solving analytically the equations, you're actually solving an approximation. The constraints are slightly not satisfied. So what you're solving is not Einstein's equations, you're solving something else that looks like Einstein's equations, but it's not quite. And this new system did not have to behave in any way nice. So typically, the departure of satisfying the constraints may be completely off with respect to Einstein's equations. So the typical way of seeing this is the following, and this can go to Maxwell, it can go to ideal MHD, etc. So you have a space of solution of the full system of equations. Then you have a subspace in it of the solutions that not only satisfy the full equations, but they are also satisfying the constraints. And of course, what you're trying to do is stay in here. But if you are slightly off this manifold, the submanifold, the constraints, then you might have a theory that does that. It completely blows away. So the trick is to try to say or ask, is there anything that I can do that, given that I started some distance off, bring it back to the constrained hypersurface? And this is what we're going to look at right now. So again, this is in the notes. So let me just give you the main ingredients. So remember what we did there? We swap, and let's going to keep the discussion in general as far as the h. We can always imagine that h is 0, and then get back to the constraint, to the harmonic. If we put h non-zero, this is what is referred to as generalized harmonic. So let's see what we did. So we had that equation with gammas, and we replaced them with h's. So what we actually are having here is the fact that we have constraints. Let me just write it this way, plus gamma a. So imagine that at some point, you choose these coordinates that satisfy this, right? Here, you have the evolution of the metric. If the metric begins to drift away from satisfying the constraints, then of this condition, then you're going to have a violation, and that violation translates into this. So this constraint, which is h plus gamma, need not be 0 throughout. But you can show, just by staring at it, that the equation with the replacement is given by simply this. Because if I replace h in here, these equations in here, then the gammas will cancel the r gammas, and then I'll have the h. So it's the same replacement, except that rather than doing by hand, allowing for some violation and then carrying it through. So this is our system. So now we want to know how do the C's evolve given that this is the effective equation that I'm solving. So what we can do now is to just take the gradient. So imagine taking the curl of this. Right, the covariant derivative of this. This gives you the covariant derivative of R. Let me start again. So again, we had this. This has to be satisfied. So imagine taking this has to be satisfied as well, but then this is the same as. So there is a way to relate the covariant derivative of RAB with the covariant derivative of R. You can replace that in here, and the equation that you end up with is the following. So this is, if you evolve the system with these equations, what is the consequence of evolving those equations on these constraints? And the consequence is that these constraints are governed by that. And we'll see this again when we discuss on Friday the analog for ideal MHD. Because we're going to play the same trick for ideal MHD to try to ensure, even though we're not going to use any specific algorithm to control the constraints, we're going to try to do it at the analytical level. So here, as it says, you have a wave equation for C equal to some source. But if your initial conditions were C is equal to 0, and the time derivative of C equal to 0, this evolves 0. So it says analytically, if you satisfy the constraints initially, they'll be propagated throughout. And this may be good, but it's not good enough, as you show in the movie. As you saw in the movie. The left-hand side went to hell, and this is what was underlying that system. So let's imagine doing something else and changing, because after all, what did we do here? At the analytical level, we just added a 0, because the constraint is supposed to be satisfied. So let's add a different type of 0, because after all, when you're desperate, you can imagine doing these kind of things. And here we add the following. So not only did we add this, but also we add an extra term that is, of course, proportional to the constraints. Again, if the constraints are satisfied, you didn't change anything. But if they are not, you actually have a different system of equations. And the question is, what is the resultant system of equations doing with respect to the constraints? If you do the same exercise, you take the divergence of this thing, tie the divergence of R with the divergence of the Ricci scalar, and go through the algebra, then this equation gets changed, and gets changed to the following. You pick up a few extra terms. So now that's what we have. And so you can analyze what is the system going to do. And so let's imagine that you started with a small constraint violation because you worked really hard, defining initial data that were consistent with the constraints. And so let's imagine that to linear order in C, this is 0 because it goes like C squared. This is 0 because it goes like C squared. Then you have that piece. So what you have to linear order is the following. where t is some vector that goes along time, or it could be any time-like vector. So now you have this equation, and this is the induced equations on the constraints. So we again have the wave equation, but you can show that if c is non-zero, what you have is a damped wave equation. This is like the telegraph equation. So this tells you that if you start with some initial violation, as you go in the future, it will be damped in a time scale given by this gamma 0. And this is what made the difference between the left side and the right side of the movie. So when are this supposed to be done? Like now? Okay, so what I'm not going to be covering, or maybe I'll say something on Friday, this is one of the formulations that actually was used to solve the binary black hole problem. There is another one that is very popular. It's called BSSN. That one is going back to the ADM, but playing essentially the same kind of trick that we're playing here. The offending term that we had before, that would have been the analog of the covariant derivative from gamma, those new variables are introduced. The evolution of those variables are obtained not only from the evolution equations that would be induced, but also adding constraints in such a way that you remove any offending terms that doesn't give you a nice hyperbolic system. So nowadays, this is kind of our workhorse. We work really hard. This is an example. We work really hard at the analytical level to try to have the cleanest possible thing, and then we fight on the algorithm level. Things were sufficiently complicated at this level that trying to do everything from the algorithmic level, in our case, did not work. So the analog of the constraint transport, so what I described on Friday, the constraint transport is absolutely required because this original system of equations is weakly hyperbolic. If you don't do constraint transport or fix the equation somehow, and we'll discuss how we can fix them at some cost that Jim alluded to that you may have to be wary about. But in that case, the constraint transport is doing something with a constraint that is fairly simple. It's the divergence of the magnetic field. It's a linear constraint. Here, we discuss what the constraints are. They're extremely complicated. It's very, very difficult. It has never been, there has never been any good or reasonable idea of how to try to implement a system in the general case that would actively enforce a constraint that's part of the algorithm. So that's why we had to step back, do something at an analytical level, and then we go forward. So with that, if you have any questions, other notes on the BSSN are in the notes. Thank you.